The morning of June 28, 1942, started like any other patrol mission over the French coast. Pilot Officer Burling Smith of 131 Squadron took off. His aircraft was a Spitfire Mark B, serial number AB910. He lifted off from the grass strip at RAF Perranporth in Cornwall. He joined 11 other Spitfires for a fighter sweep across the channel. The Rolls-Royce Merlin engine hummed with its familiar deep growl. The formation climbed through scattered clouds to 8,000 feet. Intelligence reports suggested minimal Luftwaffe activity that morning. The pilots expected a routine sortie, maybe a brief skirmish if they met a lone reconnaissance plane. Nobody suspected that within 90 minutes, one of Britain's best fighters would fall into enemy hands, almost undamaged. Smith's troubles began over Cherbourg. Suddenly, a Focke-Wulf 190 appeared out of the sun. A single cannon shell punched through his engine cowling. The Merlin coughed, belched black smoke, then ceased completely. In the sudden silence of engine failure at altitude, Smith made a quick decision. He couldn't glide back 60 miles of open water. The French coastline below was peppered with German positions. But a flat field near the village of Cretville offered his only chance. He dropped the landing gear. He held the nose up as airspeed bled away. He brought the Spitfire down in a textbook forced landing. The wheels touched the grass. The aircraft rolled perhaps 200 yards, then stopped. Smith scrambled out. He planned to torch the machine before German troops arrived. He reached for his pistol, loaded with incendiary cartridges, standard procedure for downed pilots. But a German squad materialized from the trees within seconds. Rifles pointed at his chest. The Spitfire sat behind him, slightly damaged propeller blades otherwise intact. Within an hour, Luftwaffe intelligence officers arrived from Jagdgeschwader 2's headquarters. They walked slowly around the aircraft almost reverently. The entire airframe was undamaged except for the single cannon hole in the cowling and minor propeller distortion. The landing gear hadn't collapsed. The wings showed no wrinkles or buckles. Even the radio equipment sat undisturbed in its mounting tray. One officer ran his hand along the elliptical wing's leading edge. He felt the flush riveting, something German engineers still struggled to replicate. Another peered into the cockpit, noting the gun sight, throttle quadrant, and trim wheels exactly as British pilots used them. They'd captured Spitfires before, burnt wrecks, shattered fuselages. But this machine could fly again with just an engine change and some patch welding. The intelligence value was staggering. By nightfall, a low-loader lorry arrived with a Luftwaffe technical recovery team. They drained the fuel, disconnected control cables, and hoisted the Spitfire onto the trailer. Under cover of darkness to avoid Allied reconnaissance, the convoy rumbled east towards Germany. Smith began his journey to a prisoner of war camp. He didn't know his forced landing had just given the Luftwaffe its most complete look yet at the fighter that had beaten them so badly during the Battle of Britain. The Germans had always respected the Spitfire's reputation. Pilots returning from combat over England spoke of its tight turning circle and vicious rate of climb. Messerschmitt test reports acknowledged the aircraft's superiority in certain flight regimes, but respect built on pilot testimony and second-hand intelligence differed greatly from having the actual machine available for inspection and flight testing. As AB910 crossed into Germany in early July, Luftwaffe High Command issued orders to Rechlin, the service's primary test facility. They prioritized this evaluation above nearly all other projects. They wanted precise answers: climb performance, turning radius, stall characteristics, maximum speed at altitude, and roll rate. Crucially, they wanted comparison flights against their own frontline fighters to understand exactly where the Spitfire held advantages and where German aircraft might exploit weaknesses. The captured machine arrived at Rechlin's facilities near the Müritz Lake on July 4, 1942. Technicians wheeled it into a secure hangar. Armed guards stood at every entrance. Even Luftwaffe personnel without top-secret clearance were barred. The test pilot assigned had a reputation as one of Germany's most analytical aviators. He flew with engineer's precision, not a warrior's aggression. His initial report would either confirm Luftwaffe assumptions or shatter them completely. His name was Helmut Rempel. Rempel circled the Spitfire 3 times before touching it. He'd flown Bf-109s in combat over France and Britain, accumulating 26 confirmed victories. His own forced landing in England had put him in a POW camp for 8 months. A prisoner exchange in early 1942 brought him home. The Luftwaffe immediately assigned him to Rechlin's renowned test center. His combat experience and technical understanding made him the obvious choice. Yet standing in that hangar on July 5th, examining AB910 under harsh electric lights, Rempel questioned everything German intelligence had told him about Spitfire construction and capability. The first shock came from the weight, or rather, the lack of it. Luftwaffe intelligence estimates suggested the Spitfire Mark V weighed approximately 3,200 kilos fully loaded. Rempel's team placed AB910 on calibrated scales after installing a replacement Merlin 45 engine. The reading showed 2,011 kilos with full fuel and ammunition, nearly 300 kilo lighter than German projections. Rempel did the math immediately. That weight difference translated directly into climb performance, sustained turn rate, and acceleration, all areas where the Bf-109F already struggled against Spitfires according to pilot reports. If the British fighter was actually lighter, those performance gaps would be even wider. He moved to the wings. The elliptical platform fascinated German engineers. They considered it aerodynamically ideal but impossibly expensive to manufacture. Messerschmitt had chosen a simpler straight-tapered wing for the 109 precisely because complex curves demanded excessive tooling and skilled labor. Yet here sat a mass-produced British fighter with wings that looked sculpted, not stamped. Rempel ran his fingers along the underside. He felt barely perceptible bumps where flush rivets sat. The entire lower wing surface was smoother than anything coming out of German factories. He knew skin smoothness directly affected drag, especially at high speeds. Every protruding rivet head cost kilometers per hour in maximum velocity. The British had solved the manufacturing problem German engineers still called impossible at scale. The cockpit delivered another unsettling surprise. Rempel climbed in, adjusted the seat, and examined the instrument panel. Everything was logically positioned. Throttle under his left hand, trim wheels within reach, gun sight at perfect eye level. But the visibility stunned him. The bubble canopy provided an almost unobstructed view in every direction except directly aft. He'd flown the Bf-109F extensively. Its canopy felt claustrophobic by comparison. Thick frames interrupted sightlines, and the head armor plate blocked rearward vision. In combat, seeing the enemy first often mattered more than speed or armament. If British pilots enjoyed this panoramic view while Luftwaffe pilots squinted through narrow glazing, that advantage alone might explain why Spitfires seemed to appear from nowhere. Oberleutnant Hans-Joachim Marseille, another test pilot, focused on the control system. He disconnected inspection panels and traced the cable runs. German fighters used relatively stiff control harmony, heavy stick forces requiring muscle. The British had designed something entirely different. The ailerons responded to fingertip pressure even with the aircraft stationary. Marseille pulled the stick through its full travel, feeling the resistance. Light, remarkably light. He called Rempel over. Both pilots worked the controls, exchanging worried glances. If these control forces remained light in flight, the Spitfire could achieve roll rates the Bf-109's heavy ailerons simply couldn't match. Rolling performance determined who won dogfights. The fighter that could reverse bank direction faster controlled the engagement. The engineering team dismantled panels across the fuselage. They photographed every structural detail. They discovered stressed skin construction techniques more advanced than German methods. The metal skin itself carried aerodynamic loads requiring heavy internal frameworks. The British had essentially built a flying semi-monocoque structure, saving weight while maintaining strength. German aircraft still relied on traditional framework construction. The weight penalty was substantial, but Messerschmitt and Focke-Wulf engineers had insisted the British approach was too complex for mass production. Yet here sat proof that British factories were churning out these sophisticated structures in quantities exceeding Luftwaffe fighter production. Rempel compiled his preliminary ground inspection report that evening. The conclusions were blunt. Every pre-war assumption about Spitfire construction had been wrong. The aircraft was lighter, more aerodynamically refined, better designed for pilot efficiency, and more cleverly engineered than intelligence estimates suggested. And they hadn't even started the engine yet. The actual flight testing would either ease German concerns or confirm that the Luftwaffe faced an opponent even more capable than the one that had cost them the Battle of Britain. The security protocols surrounding AB910's flight testing exceeded those protecting Germany's own experimental aircraft. Reichsmarschall Göring himself issued orders. No mention of the captured Spitfire could appear in any written communication outside the highest command levels. Rechlin's commander established a perimeter around the test hangar. Gestapo officers checked credentials of anyone approaching within 200 meters. The Luftwaffe feared Allied intelligence might learn about the intact capture and launch a bombing raid specifically to destroy this single aircraft. One Wellington or Mosquito finding Rechlin on a clear night could erase months of research in seconds. Preparing the Spitfire for flight demanded 3 weeks of meticulous work. The replacement Merlin engine pulled from a crashed Mark V found in a French field required complete inspection and testing. German technicians had minimal experience with Rolls-Royce engines. The Merlin's sophisticated two-stage supercharger differed substantially from simpler units fitted to Daimler-Benz power plants. Each component needed verification. The coolant system used a glycol mixture slightly different from German specifications. The ignition timing had to be set precisely according to captured British technical manuals. Even the propeller presented challenges. The constant speed unit operated on hydraulic principles German engineers found unnecessarily complex compared to their own electric controls. Painting the aircraft sparked heated debate. Some argued for keeping it in RAF camouflage for potential deception operations, perhaps flying it low over occupied territory to confuse Allied pilots, or even attempt an infiltration mission. Others insisted on applying full Luftwaffe markings to avoid friendly fire during test flights. The compromise satisfied nobody. They painted prominent black and white Balkan crosses on the fuselage and wings while retaining most of the original RAF camouflage. Large yellow identification panels were added to the nose and rear fuselage, the Luftwaffe's standard marking for aircraft operating in the Eastern Theater. Though this Spitfire would never see Russia, ground crews also painted White 14 on the fuselage sides, designating it as an aircraft in the Rechlin test inventory. The hybrid appearance looked bizarre, a visual symbol of the aircraft's confused identity. British engineering presented an unexpected complication. The Merlin engine was designed to run on 100-octane aviation petrol, a grade Britain received in vast quantities from American refineries. Germany's synthetic fuel production struggled. Their highest grade, C3, rated at 96 octane, was close but not identical. Engineers calculated using C3 fuel would reduce engine performance by approximately 3 to 4%, particularly affecting maximum boost pressure at altitude. This meant any test results would actually understate the Spitfire's true capabilities. When Rempel learned this, he insisted the discrepancy be noted prominently in all reports. If the Spitfire demonstrated superiority while running on suboptimal fuel, that made the findings even more alarming. Selecting the test pilot roster required careful consideration. Rempel would fly the initial evaluation sorties, but Rechlin's commander wanted multiple pilots for independent assessments. They chose 3 additional aviators. Marseille, who'd examined the control systems so thoroughly. Hauptmann Emil Lang, a former instructor with over 3,000 flight hours who could assess handling qualities objectively, and Oberleutnant Franz Stiegler, a combat veteran from Jagdgeschwader 27 who'd fought Spitfires over Malta and could compare the real aircraft against his combat memories. Each pilot studied AB910's technical manual, a captured RAF document that German translators worked through page by page, converting measurements and terminology. The weather turned uncooperative in late July. Heavy cloud and intermittent rain kept the Spitfire grounded for 6 consecutive days. Rempel used the delay for ground runs, advancing the throttle while mechanics monitored engine temperatures and pressures. The Merlin's distinctive sound, higher pitched than the Daimler-Benz engines he knew, echoed across Rechlin. Other test pilots stopped to listen. That sound had terrified German bomber crews over Britain 2 years earlier. The acoustic signature of Spitfires diving to attack. Hearing it now, produced by a captured British engine wearing Luftwaffe crosses, created a surreal atmosphere. One mechanic later wrote in his diary that the engine note made him profoundly uneasy, as though they'd captured something that didn't want to be caged. On July 29, 1942, conditions finally cleared. Morning mist burned off by 9 p.m., leaving calm air and unlimited visibility. Rempel completed his pre-flight inspection, climbed in and strapped himself in. Ground crew removed the chocks. This would be a cautious first flight. Takeoff, climb to 3,000 meters, basic handling checks, then landing. No aerobatics, no high-speed runs. Nothing that might stress the airframe that had already survived one forced landing. The intelligence gained justified the conservative approach. After confirming the aircraft was fundamentally airworthy, Rempel advanced the throttle smoothly. He felt the Merlin's power build through the airframe. The Spitfire accelerated faster than he'd anticipated, distinctly quicker than the Bf-109F he'd flown the day before for comparison. The tail came up at 60 km/h. Suddenly, he could see straight ahead down the grass runway instead of peering around the nose. At 140 km/h, the fighter simply lifted itself into the air without any conscious back pressure on the stick. He'd expected to haul back to force the aircraft off the ground the way German fighters demanded. The sensation was unsettling and exhilarating simultaneously. Climbing through 1,000 meters, Rempel began gentle exploration of the controls. He'd read the captured pilot's notes thoroughly, knowing stall speeds and handling parameters. But numbers on paper conveyed nothing about how an aircraft actually felt. He rolled into a shallow bank to the left. The ailerons responded with almost shocking immediacy. Barely any stick movement produced a crisp roll rate. He reversed the bank to the right. Same response. Light, precise, no lag between input and reaction. The Bf-109 required firm stick pressure and deliberate muscle to achieve similar roll rates, especially above 300 km/h, where aerodynamic loads stiffened the controls considerably. This British fighter rolled like it was reading his mind rather than waiting for physical inputs. At 2,000 meters, he tried the first real turn, a gentle 30-degree bank, maintaining altitude with slight back pressure. The Spitfire carved through the air smoothly, no buffeting, no tendency to drop a wing or skid outward. He tightened the bank to 45 degrees, still smooth. Now 60 degrees, pulling harder on the stick, feeling the G-forces press him into the seat. The turn radius shrank dramatically, yet the aircraft remained stable and controllable. The buffet that warned of approaching stall never materialized. He glanced at the airspeed indicator, 210 km/h, and still flying comfortably in this steep turn. German fighters would be shaking and protesting at these angles and speeds, demanding constant corrections to prevent a snap roll or departure from controlled flight. Something else caught his attention. The elevator response felt perfectly harmonized with the ailerons, neither control dominating, both working together naturally. German aircraft typically had heavier elevator forces than aileron forces or vice versa, creating a slight mismatch pilots learned to compensate for unconsciously. The Spitfire's designers had achieved genuine harmony across all three axes, rolling, pitching, and yawing forces, all balanced proportionally. The psychological effect was profound. Rempel realized he wasn't fighting the aircraft or managing its quirks. He was simply thinking about where he wanted to go, and the Spitfire went there. This was what the RAF meant by the Spitfire's forgiving nature and intuitive handling. He climbed to 3,000 meters and attempted some vertical maneuvers. A half loop, up and over the top, rolling inverted momentarily before completing the curve. The Merlin's -G carburetor cut out briefly at the top of the loop, exactly as the technical manual warned, causing a momentary cough before +G loading resumed. German fighters used fuel injection systems that avoided this problem, but the carburetor issue seemed a minor inconvenience rather than a combat limitation. Pilots could simply roll inverted before pulling through, maintaining +G throughout the maneuver. The climb rate during the loop's initial phase impressed him more than the carburetor's weakness. The Spitfire shot upward aggressively, converting airspeed to altitude with remarkable efficiency. Throttle response deserved special attention. Rempel had flown dozens of fighter types. Most exhibited noticeable lag between throttle movement and engine power change. The Merlin reacted almost instantly. Advance the throttle, immediate power increase. Reduce it, immediate power decrease. This mattered enormously in combat, where pilots constantly adjusted power to manage energy and position. A fighter that responded sluggishly forced its pilot to anticipate power, need seconds in advance. The Spitfire let its pilot react in real time to changing tactical situations. Combined with the light controls and tight turning radius, this meant a Spitfire pilot could transition between different flight regimes, climbing, diving, turning, accelerating with minimal delay or planning. The aircraft simply did what its pilot asked when he asked it. Rempel deliberately pulled the nose up sharply, bleeding off airspeed to explore stall characteristics. The airspeed indicator wound down, 180, 160, 140, 120 km/h. The aircraft began to buffet gently, giving ample warning. At 110 km/h, the nose finally dropped, but the stall was gentle and predictable. Forward stick, add power, and the Spitfire recovered immediately without any drama. No wing drop, no incipient spin, just a straightforward aerodynamic stall any pilot could manage easily. German training aircraft often exhibited vicious stall behavior to teach respect for the edge of the flight envelope. The Spitfire's docile stall meant combat pilots could fly right to the edge without fearing loss of control. After 40 minutes, the planned duration for this first sortie, Rempel returned to Rechlin and set up for landing. The approach speed felt slow under 150 km/h, giving him plenty of time to adjust and align with the grass runway. The view over the nose remained excellent, even with the tail dragger configuration. Touchdown was smooth, the aircraft settling onto the grass without bouncing or floating. He rolled to a stop and shut down the engine. Ground crew rushed toward the aircraft as Rempel sat quietly in the cockpit for several seconds, processing what he'd just experienced. Then he climbed out and walked directly to the operations office without speaking to anyone. His preliminary flight report took 3 hours to write and concluded with a sentence that sent shockwaves through Luftwaffe High Command. This aircraft is superior to the Bf-109F in every combat-relevant parameter except maximum speed above 6,000 meters. The comparative trials began on August 3, 1942, with Rechlin's most experienced combat pilots rotating through both the captured Spitfire and frontline Luftwaffe fighters. The methodology was rigorous and scientific. Timed climbs to specific altitudes, measured turning circles at various speeds, acceleration runs, and mock dogfights with gun cameras recording every engagement. Each test was repeated multiple times to eliminate anomalies. The Luftwaffe needed quantifiable evidence, not subjective pilot opinions, though those opinions proved remarkably uniform regardless of which aviator was flying. The first head-to-head matchup pitted AB910 against a Bf-109F4, the Luftwaffe's primary frontline fighter in mid-1942. Rempel flew the Spitfire while Marseille took the Messerschmitt. Both aircraft took off simultaneously and climbed to 5,000 meters before beginning their engagement. The test protocol called for a neutral start, both fighters flying parallel at cruise speed before initiating a turning fight. On signal, both pilots broke hard toward each other. Within 2 complete turns, Rempel had positioned the Spitfire onto Marseille's tail. The gun camera footage showed the Bf-109 frantically trying to outturn the British fighter, but the geometry remained hopeless. The Spitfire's tighter turning radius meant every 360-degree rotation put it slightly closer to a firing position. After 6 turns, Marseille's only option was to dive away at full throttle, attempting to use the Bf-109's superior dive acceleration to break contact. They repeated the engagement 5 times with different starting positions. The result varied only in how long the Bf-109 survived before the Spitfire achieved a theoretical kill. In level turning combat, the German fighter was simply outclassed. The data confirmed what combat reports had suggested. A Spitfire pilot who maintained discipline and stayed in the horizontal plane would defeat a Bf-109 pilot of equal skill almost every time. Marseille's post-flight comments were professionally matter-of-fact but devastating. Against a Spitfire, we must never enter a sustained turn. Our only advantages are initial acceleration in the dive and marginally better high-altitude performance above 7,000 meters. We must fight vertically, never horizontally. The climb rate comparison delivered equally sobering results. Both aircraft started from ground level and climbed at maximum continuous power to 6,000 meters. The Spitfire reached altitude in 6 minutes and 42 seconds. The Bf-109F required 7 minutes and 18 seconds, a 36-second deficit that translated into roughly 800 meters of altitude advantage in combat. If a mixed formation of Spitfires and Bf-109s began climbing simultaneously from the same altitude, the British fighters would enjoy a massive positional advantage by the time they met in combat. German pilots had developed tactics to compensate, typically gaining altitude well before an engagement and using that height advantage to offset the Spitfire's superior climb performance. But this required knowing where the enemy would appear, something rarely possible in fluid combat situations. Roll rate testing produced perhaps the most alarming data. Engineers mounted high-speed cameras to capture the exact time required for each aircraft to complete a full 360-degree roll at various airspeeds. At 400 kilometers per hour, a typical combat speed, the Spitfire completed the roll in 1.8 seconds. The Bf-109F needed 2.4 seconds. That 0.6-second difference seemed trivial on paper, but in combat, it determined who could reverse bank direction quickly enough to track a maneuvering opponent. The Spitfire pilot could roll inverted, pull through to reverse direction, and roll upright again before the Bf-109 pilot had completed his reversal. This single characteristic explained why experienced Luftwaffe pilots reported feeling perpetually behind the energy curve when fighting Spitfires. They were flying an aircraft that responded fractionally slower to every control input. The captured Spitfire then faced the Focke-Wulf FW-190, which had entered service just months earlier. German pilots considered the FW-190 clearly superior to the Bf-109 in most respects. Better roll rate, heavier armament, superior high-speed handling. Surely this newer fighter would match or exceed the Spitfire's capabilities. Stiegler flew the FW-190 while Lang took the Spitfire. The engagement began identically to the Bf-109 tests. The FW-190 performed better than the Messerschmitt initially. Its excellent roll rate let Stiegler reverse direction quickly to counter Lang's maneuvers. But after 3 complete turns, the Spitfire still ended up in a firing position. The British fighter's slightly tighter turning radius eventually overcame the FW-190's roll advantage. However, the FW-190 demonstrated clear superiority in other regimes. Its dive performance exceeded both the Spitfire and the Bf-109 substantially. In level flight above 5,000 meters, the Focke-Wulf was faster by approximately 25 km/h. The German fighter also carried far heavier armament, 4 20mm cannon plus 2 machine guns compared to the Spitfire's 2 cannon and 4 machine guns. In a single firing pass, the FW-190 delivered nearly double the projectile weight. This suggested tactical solutions. FW-190 pilots should avoid turning engagements entirely, instead using speed and diving attacks to engage Spitfires on their own terms, breaking away before the British fighter could force a turning fight. The test team also evaluated the Spitfire against the Bf-109G, which had just begun reaching frontline units. The Gustav variant carried a more powerful engine than the Friedrich, and engineers hoped this would close the performance gap. The results were mixed but ultimately disappointing. The Bf-109G climbed fractionally faster than the Spitfire below 4,000 meters. But above that altitude, the British fighter regained its advantage. Turning performance remained decisively in the Spitfire's favor. The Gustav's heavier armament and improved engine came at a weight penalty that worsened its already marginal handling characteristics. Rempel's assessment was blunt. The 109G is an improvement over the Friedrich in armament and climb, but it remains inferior to the Spitfire in the turning combat that dominates engagements below 6,000 meters. The comprehensive test data landed on desks throughout Luftwaffe High Command in late August 1942, accompanied by gun camera footage that made the performance gaps viscerally obvious. Senior officers gathered in briefing rooms to watch film of the captured Spitfire, systematically outmaneuvering every German fighter type. The implications extended far beyond acknowledging British engineering excellence. These findings demanded immediate tactical revisions, training modifications, and operational doctrine changes across every fighter unit from Norway to North Africa. The Luftwaffe had spent 3 years developing tactics based partly on assumptions about Spitfire capabilities, assumptions now proven dangerously wrong. General der Jagdflieger Adolf Galland received the complete Rechlin report on August 27th. Galland had led fighter units throughout the Battle of Britain and understood Spitfire capabilities from brutal first-hand experience, but even he found the measured data shocking. The turn radius differential was worse than combat pilots had estimated. The roll rate advantage was larger. The climb performance gap was wider. He immediately convened a conference of Geschwader commanders to discuss tactical responses. The meeting lasted 2 days and produced a revised fighter combat manual distributed to every Geschwader by mid-September. The new doctrine acknowledged uncomfortable truths and mandated specific tactical approaches to offset German fighters' measured disadvantages. The core principle was simple: never fight the Spitfire on its terms. German pilots were explicitly forbidden from entering sustained turning engagements unless they held overwhelming numerical superiority. The revised manual stated this bluntly: a Spitfire will outturn any Luftwaffe fighter currently in service. Pilots who attempt turning combat against equal or superior numbers of Spitfires will be shot down. Instead, German fighters were instructed to exploit their specific advantages ruthlessly. The Bf-109 should use its superior high-altitude performance and dive characteristics, attacking from above, making a single firing pass, then diving away before the Spitfire could respond. The FW-190 should similarly rely on speed and diving attacks, never slowing down enough to let a Spitfire force a horizontal engagement. Training syllabuses changed across Luftwaffe flight schools. New pilots had always learned basic dogfighting techniques: how to turn inside an opponent, how to lead a target, how to manage energy. The post-Rechlin curriculum de-emphasized turning combat entirely when the opponent was identified as a Spitfire. Instead, instructors drilled students on boom and zoom tactics: gain altitude, dive on the enemy, fire, extend away, climb back to altitude, repeat. This vertical fighting style suited German fighters' strengths, but required exceptional discipline. Inexperienced pilots instinctively wanted to follow a damaged enemy by turning after them, which frequently proved fatal if the damaged aircraft was a Spitfire feigning vulnerability. The Rechlin data also influenced aircraft development priorities. Focke-Wulf and Messerschmitt engineers received explicit guidance to prioritize high-speed performance and climb rate in future fighter variants, even if this came at the cost of turning ability. The thinking was pragmatic. German fighters would never outturn a Spitfire through incremental improvements, so attempting to compete in that regime wasted resources. Better to enhance the characteristics where German aircraft already held advantages, widening those performance gaps to create clearer tactical options for pilots. This philosophy influenced designs like the later Bf-109K variants and the TA-152, both optimized for high-altitude interception rather than low-level dogfighting. The captured Spitfire had taught German designers that such universal superiority was unrealistic, given industrial and resource constraints. Better to dominate a narrow performance band than be mediocre everywhere. Intelligence gathering received new urgency. If one Spitfire variant could demonstrate this level of superiority, what might improved versions achieve? The RAF was known to be developing new marks continuously. The Rechlin test team's final report specifically warned that the captured Mark V likely represented the middle of the Spitfire's evolutionary range, not its peak. British engineers would certainly be working on more powerful engines, improved aerodynamics, and better armament. Luftwaffe intelligence services were ordered to prioritize information about Spitfire development with particular emphasis on the rumored Griffin engine variants that might render current German fighters completely obsolete. Every captured document, every interrogated RAF prisoner, every agent report from Britain received scrutiny for hints about future Spitfire capabilities. The tactical shift wasn't purely defensive. German commanders recognized that understanding the Spitfire's specific weaknesses, few as they were, could enable offensive exploitation. The Rechlin test had identified that the Merlin engine's negative G carburetor limitation remained unresolved in the Mark IV Spitfire. Pilot who bunted forward into negative G would experience momentary engine cutout. Luftwaffe pilots were instructed to watch for this vulnerability. If a Spitfire pursued a diving German fighter, the RAF pilot would instinctively push forward on the stick to follow, causing his engine to cut out briefly. That fraction of a second might allow the German pilot to extend beyond firing range or reverse the engagement. It was a slim advantage, but combat was won through accumulation of slim advantages. Formation tactics evolved as well. Pre-war German doctrine favored tight formations that maximized defensive firepower, but reduced individual maneuverability. Against Spitfires, this proved suicidal. A formation that couldn't maneuver played directly into the British fighters' strengths. The revised doctrine mandated loose formations with wider spacing, allowing each pilot maximum freedom to maneuver independently. The classic four-aircraft swarm formation was retained, but with increased vertical separation, ensuring that if the lower pair engaged Spitfires in turning combat, the upper pair could dive down for slashing attacks. This sacrificed some formation cohesion, but acknowledged the reality that formation integrity mattered less than giving each pilot the tactical flexibility to avoid Spitfire turning. Traps, fighter units operating in different theaters received customized guidance. In the Mediterranean, where combat typically occurred below 4,000 meters in hot air that reduced engine performance, Spitfires held maximum advantage. German fighters in North Africa and Sicily were instructed to avoid combat entirely, unless holding decisive positional superiority. On the Eastern Front, where Soviet fighters generally lacked the Spitfire's sophistication, the tactical changes mattered less. Over Western Europe, where RAF Spitfire squadrons dominated, Luftwaffe fighters increasingly shifted to purely defensive roles, intercepting bomber formations rather than seeking fighter engagements. The psychological impact was profound. Within months of the Rechlin testing, German fighter pilots viewed encounters with Spitfires as dangerous, necessities to be avoided when possible rather than opportunities for victory. AB910's career in German hands extended through the autumn and winter of 1942, though its role shifted from pure testing to operational deception and specialized training. The Luftwaffe recognized that simply having a flyable Spitfire offered strategic opportunities beyond technical evaluation. The aircraft became a tool for psychological operations, pilot familiarization, and combat tactics refinement. Yet every flight carried risk. A single catastrophic failure would destroy this irreplaceable intelligence asset, ending the programs that depended on it. Through September and October, selected Luftwaffe pilots from frontline units rotated through Rechlin for familiarization training. Each pilot spent several hours examining AB910 on the ground before flying it for approximately 30 minutes. The goal was simple: let combat pilots who would face Spitfires regularly experience the aircraft from inside the cockpit. These flights provided psychological preparation as much as tactical insight. German pilots who'd only fought against Spitfires often developed exaggerated respect, bordering on fear. Actually flying the machine demystified it somewhat. Yes, it was an exceptional aircraft, but it wasn't supernatural. It had limitations, quirks, and vulnerabilities that could be exploited by a knowledgeable pilot. The Luftwaffe also used AB910 for practice interceptions, helping train German pilots to recognize and counter Spitfire tactics. A typical training mission involved AB910 taking off and flying defensive patterns, while BF-109s or FW-190s attempted interceptions. The exercise reversed the usual dynamic. Instead of German fighters being defensive against superior British aircraft, they practiced offensive tactics against an actual Spitfire. Pilots learned to recognize the specific moment when a Spitfire's tighter turning radius would trap them in a losing engagement, developing the instinct to disengage before reaching that point. They practiced the split-second timing required to dive away from a pursuing Spitfire before it could line up a firing solution. Gun camera footage from these training sorties was distributed to operational units as instructional. Material intelligence services proposed using AB910 for penetration operations over Britain, flying the Spitfire at low level to infiltrate British airspace, photograph installations, or drop agents. The operational planning reached advanced stages before cooler heads prevailed. The risk was absurd relative to the potential gain. RAF fighters would likely identify AB910 as hostile, despite its Spitfire profile, simply because any aircraft approaching from occupied Europe was assumed enemy until proven otherwise. British radar operators and ground observers knew their own aircraft's operating patterns. A lone Spitfire appearing unexpectedly would trigger investigation and probable interception. Even if the mission succeeded once, the aircraft would almost certainly be lost, ending all ongoing research. The proposal was quietly shelved. The Spitfire also served less glamorous but more practical purposes. Engineers used it extensively to test captured British equipment: radios, gun sights, oxygen systems, even ammunition. Whenever German forces recovered RAF equipment from crash sites, technicians needed to understand how it functioned and whether it offered any advantages over Luftwaffe equivalents. Having a flyable Spitfire meant they could install these components in their original airframe and evaluate them under realistic conditions. For example, the British Mark II gyroscopic gun sight recovered from a crashed Hurricane was fitted to AB910 and flown against maneuvering targets. German pilots found it marginally superior to Luftwaffe reflector sights at high deflection angles, leading to accelerated development of indigenous gyroscopic sight designs. By early 1943, AB910 had accumulated approximately 80 flight hours under German operation. The airframe was showing signs of stress. The replacement Merlin engine had never been properly overhauled. just patched together from components scavenged from multiple wrecked aircraft. Oil consumption was increasing. Cylinder head temperatures ran hotter than specifications. The landing gear had developed a worrying tendency to hang up slightly during retraction. Each flight risked mechanical failure that might damage or destroy the aircraft. Rechlin's commander faced an increasingly difficult decision: continue flying the Spitfire and accept the rising probability of loss, or ground it permanently and preserve it as a static exhibit. The decision was made for him by Allied bombing. On the night of April 17, 1943, RAF Bomber Command launched a heavy raid against targets in northern Germany. Rechlin wasn't the primary objective. Several bombers, damaged by flak and disoriented by clouds, jettisoned their loads randomly while trying to reach the coast. One stick of bombs fell across Rechlin's dispersal area. AB910 sat in a supposedly secure hangar, but a single 500-pound bomb penetrated the roof and detonated 15 meters from the aircraft. The blast wave crumpled the Spitfire's fuselage, shattered the canopy, and tore off the port wing. Shrapnel riddled the Merlin engine. When the dust cleared, AB910 was recognizable as a Spitfire, but it would never fly again. German photographers documented the wreckage meticulously. Technicians salvaged every component that might still yield intelligence value. The engine was shipped to Daimler-Benz for detailed teardown analysis. The control systems were preserved for continued study. The remains of the airframe went to a Messerschmitt facility, where engineers used it as a reference for stress analysis and structural design research. Even destroyed, the captured Spitfire continued serving the Luftwaffe's technical intelligence needs. The gun camera footage, test reports, pilot assessments, and engineering data remained in active use through the war's end, informing every subsequent fighter development program and tactical revision. One aircraft captured through the accident of a forced landing had provided Germany with an intelligence windfall that shaped Luftwaffe operations for 3 years. That it ultimately fell to a randomly jettisoned bomb represented the kind of bitter irony that characterized the entire war. Invaluable intelligence assets destroyed by the ordinary chaos of industrial-scale combat. The legacy of AB910's capture and testing rippled through German military aviation long after the twisted wreckage was carted away from Rechlin's bomb-damaged hangar. The data extracted from those 80 flight hours influenced aircraft design philosophy, tactical doctrine, and strategic planning in ways that persisted until Germany's surrender in May 1945. The Spitfire's measured superiority forced uncomfortable institutional reckonings within the Luftwaffe. Acknowledgments that German engineering, while sophisticated, had been outpaced in specific critical areas by British design teams working with different priorities and methodologies. Fighter development programs absorbed the lessons directly. When Messerschmitt's design bureau began work on what would become the Me-262 jet fighter, engineers deliberately prioritized speed above all other characteristics. The Rechlin data had demonstrated that trying to match the Spitfire's turning performance was futile. German piston engine fighters simply couldn't achieve that combination of lightweight, powerful engine and aerodynamic refinement. Jets offered a different path entirely, using raw speed to dictate engagement terms. The Me-262's design philosophy, extreme speed, allowing the pilot to choose when to fight and when to disengage, came directly from lessons learned by flying AB910. If you couldn't outturn a Spitfire, you needed to be fast enough that turning ability became irrelevant. Tanks designed for the Focke-Wulf Ta-152 high-altitude fighter similarly reflected Rechlin's findings. Rather than attempting an all-around superiority fighter, Tank focused obsessively on the one regime where German fighters had demonstrated a measurable advantage, performance above 7,000 meters. The Ta-152H variant featured an extremely long-span wing and a pressurized cockpit optimized entirely for stratospheric interception work, where Spitfires showed relative weakness. This represented a fundamental philosophical shift from pre-war thinking, which had sought fighters capable of dominating across all altitude bands and combat situations. The captured Spitfire had taught German designers that such universal superiority was unrealistic given industrial and resource constraints. Better to dominate a narrow performance band than be mediocre everywhere. Tactical doctrine evolution continued throughout 1943 and 1944 as the Rechlin principles filtered down to operational units. Experienced Luftwaffe pilots developed sophisticated techniques for defeating Spitfires, despite their aircraft's measured disadvantages. These tactics relied on exploiting the specific scenarios where German fighters retained advantages. Initial acceleration in the dive, slightly better high-speed handling in the FW-190's case, superior armament weight. Pilots learned to treat every engagement as a hit-and-run operation, never remaining in the combat area long enough for Spitfires to force the horizontal turning fights where British aircraft excelled. The kill-to-loss ratios never favored the Luftwaffe over Western Europe, but they might have been catastrophically worse without the tactical adjustments informed by AB910's test program. The intelligence value extended beyond pure performance metrics. Having intimate familiarity with Spitfire systems helped German engineers develop specific countermeasures and exploitation tactics. For instance, detailed study of the British IFF identification system examined thoroughly on AB910 helped Luftwaffe signals intelligence teams identify and track RAF formations with greater accuracy. Understanding the Spitfire's radio equipment revealed its operational range limitations, allowing German commanders to position fighters at distances where Spitfire escorts couldn't effectively communicate with their bases. These second-order intelligence benefits, extracted from meticulous examination of systems and components, proved nearly as valuable as the flight performance data. The captured aircraft also served as a cautionary tale for Luftwaffe security services. If a single Spitfire landing intact could provide such comprehensive intelligence to Germany, what might Britain learn from captured Luftwaffe aircraft? This prompted significantly enhanced security protocols around aircraft recovery and pilot rescue. German units received explicit orders to destroy damaged aircraft more thoroughly, rather than risk them falling into enemy hands repairable. Pilots were instructed to use incendiary devices and small demolition charges to ensure crashed fighters couldn't be reconstructed. Intelligence officers interrogated returning pilots extensively about what British forces might have learned from any Luftwaffe aircraft abandoned in Allied-controlled territory. British intelligence remained largely unaware of AB910's capture and comprehensive testing throughout the war. Pilot Officer Burling Smith, the unfortunate pilot who'd made that forced landing near Cherbourg, spent the remainder of the war in POW camps and never learned that his aircraft had become Germany's most studied British fighter. Post-war, when RAF intelligence officers compiled histories of technological exchange during the conflict, they discovered documents referring to extensive Luftwaffe testing of a captured Mark III. The revelation prompted immediate concern about what tactical advantages Germany might have gained, though by that point the war had ended, and the question was academic. British aircraft designers were surprised to learn how accurately German engineers had mapped the Spitfire's performance envelope. The Rechlin data matched the RAF's own testing results almost perfectly. The capture influenced one final unexpected domain: post-war aviation development. When Allied intelligence teams swept through defeated Germany in 1945, they recovered enormous quantities of Luftwaffe technical documents, including the complete Rechlin test reports on AB910. British and American engineers studied these documents carefully. Less for what they revealed about the Spitfire — the RAF knew its own fighter intimately — than for what they exposed about German testing methodology and analytical approaches. The meticulous, systematic way engineers had evaluated AB910 impressed Allied aviation specialists. The test protocols, data recording methods, and comparative analysis techniques influenced post-war military aviation testing standards in both Britain and America. In a strange twist, the Germans had created an intelligence document about a British aircraft that ultimately taught the victors lessons about proper test and evaluation procedures. The broader lesson transcended any single aircraft or tactical adjustment. AB910's capture demonstrated that technological intelligence could be as war-changing as signals intelligence or human espionage. One intact machine methodically evaluated provided insights that shaped an entire Air Force's doctrine and development for years. The principle applied beyond fighters to tanks, radar systems, encryption devices. Any technology where understanding the opponent's capabilities influenced your own design choices and operational planning. Modern military intelligence services trace certain methodologies directly to Second World War programs like the Rechlin evaluation of captured aircraft. That legacy, built on the accident of one RAF pilot's forced landing in occupied France, represents AB910's final and most enduring contribution to aviation history.